Welcome to week 12. My video's kind of weird today. Let's go. Oh, there we go. That's what it is. It's a little smaller. There we go. So, this week we're going to cover convolutional neural networks. Convolutional is just a way to sum up uh, um, an image, I guess. Convolutional neural networks. So when I learned it, I just looked at the slide. I learned it from one of the classes I took on convolutional networks. I think we had one or two slides, and then math for the rest of the whole, like 2 weeks. Convolutional neural networks, they've been around for a while, but they have changed a lot of the way that machine learning works and the way we think about computers. Now, why is this? Well, so humans, again, we go back to neuroscience. Humans have a huge visual processing cortex. Okay, so I don't know. I have a poodle, Lucky. Come here, baby. Come here, Lucky. So here's my dog. This is Lucky, everyone. Let me see if I can get him off the camera. This is Lucky. Say hi to the camera. There he is. All right, Lucky. Yes. So dogs, while they're nuts, they don't have the same visual processing cortex. They don't have the same visual system that we do. Yes, they don't. So dogs see their world, they see their reality through smell. Okay, so dogs, their world is defined by a sense of smell. Okay, us Homo sapiens, us humans, our world is defined by visual processing or visual cortex. And that really sets us apart from most other animals on this planet. That is the way we process information visually. They say a picture is worth 1,000 words. Well, that's more than true with humans. With other animals, that's not necessarily true. With CNN, convolutional neural networks are designed to deal with image data, videos. You can use it for other things, which we'll talk about here. But that is what made CNN so changing. When you use Google Translate, take a picture of, something in French and translate it to English, that's a CNN. So I guess let's get started. Let's go over the review and foundations, architecture of CNN. Some of the stuff at the end, I'm going to go over different libraries and like different, like ResNet and VG. As long as you're just kind of aware there's different libraries and different networks, you're good. You can always Google, hey, what's the difference between ResNet and VGG? What's the difference between, for example, TensorFlow and PyTorch? But the thing is, if you don't understand the big picture CNN, then you're at a huge loss. And I also want to cover kind of some maybe applications of CNNs. So one use that I use CNNs for is that during COVID, somebody released a data set of chest X-rays that were positive for COVID. I think it was COVID. Maybe it was the flu. I don't remember. A couple of years ago. And so I use CNN to kind of detect whether or not that X-ray was, a pneumonia, a flu, COVID, or if it was just a healthy X-ray. Now, why would I do this? Because again, the CNN can't really do anything. It can't prescribe drugs. I mean, what is the point of this, Richard? What is the end product? How is it going to help business? Well, what if you have maybe a third world country that doesn't have access to radiologists in a timely manner? So that country maybe is producing 10,000 chest X-rays. X-rays are a relatively cheap and easy method to do. You're producing 10,000 X-rays, but they only get read on the weekend. They only get read once a week. Well, if we had a CNN, it could look at these chest X-rays and say, hey, these need to be read sooner than later. And the ones that read sooner, read by a radiologist, said, hey, there's something wrong here. Let's get this person on this antibiotic, and we can save thousands of dollars. There's one great example of that. I'm on a project right now. So what happens right now is if you go to the urgent care, oh, I have chest pain. They're going to order an ultrasound on you. They're going to order lab works. They're going to order everything. Now, I don't remember the exact number, but how many people do you think go to the hospital or quick care for chest pain actually have a heart attack? Come on, take a guess. I think it's like 30 or 40%. The rest of it is just indigestion. So it's a huge cost. You know, you eat a lot of spicy food. You know, you have that Thai chili that we all love. You eat that Thai chili, you put it on your, I don't know, food, and then you go to the hospital for chest pain. Well, wouldn't it be nice if a doctor could just put a probe down instead of having to call somebody and say, oh my God, you're having a heart attack. Oh my God, you're okay. I mean, if he could do it right then, right there, instead of having to outsource to, they're called echo techs, cardiovascular techs, or RDCS. So, you know, what happens right now is that if a doctor says, hey, you have a heart attack, or I think you're having a heart attack, let's get somebody to come in here and do blood work. Let's call this ultratech person. They come in, they do a scan. That scan goes over to radiology. It has to be set. It's a huge process. It's a huge process. And there should be some type of gate, or there should be some type of system in there that says, hey, yes, call an expert. No, don't call an expert. You know, and that's what we're trying to use CNNs for right now. As an undergraduate, I use CNNs to classify variants, which we'll talk about. So there's a lot of business applications in these things. So let's talk about big picture idea. So convolutionals, okay. Oops, sorry, I just loaded a word, which is not what I wanted to do. Okay, what do I say? It uses a special technique, which has a space in it, convolutions. Now, mathematics convolution is mathematical operation on two functions that produces a third function, blah, 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 nobody cares. Okay, we can kind of see that if we summarize what these four right here, 1, 2, 3, 4, we get 4. We summarize these 3, guess what, we get 3. And I think we go down to the next layer right here. Is that how we're doing it? Or maybe just 4, I don't know. And you see it, at the end of the day, we're basically kind of compressing that data. Okay, and that's maybe not the best word to use, but this is what a convolution does. We look at each section and we kind of get a summary of what's in there. And this will become clearer here in a minute or two. It becomes really complex really quick. So let's talk with, this is kind of a person with a flashlight. That's the idea. So that's always the analogy that people use. So a convolutional layer. Imagine, you know, you have a bunch of little flashlights. I have a flashlight here somewhere, and that you shine it on a picture in the dark. So you can only see a small part of the picture at a time. So each the flashlight is designed to only light up, you know, the first right part. As you saw with that convolution, it goes over and over and over. And when you see that flashlight, you're like, well, you don't know what the whole picture's of, but you're using that flashlight. Oh, hey, there's a corner. Oh, there's a bumper. If it's a bumper, maybe it's a car. You keep going. And you create a bunch of little details. So I have a picture. Let's see if I can get this on camera. And I'm just using a flashlight to look at the picture. And so now if I'm looking at a picture of a car, oh, look, I might see a window. I might see a side mirror, a bumper, a tire. Okay? That's kind of how humans work. That would be maybe bottom-up processing. I mean, we take an image and we break it down to these convolutions. But the problem is, if we look at something here, we want to look at this guy swimming. And what do we notice? Well, we want to focus on that person swimming in the water. We don't care about all these people in the background. So even with the convolution, we still have a lot of detail. And we want to make it smaller. We want to analyze that data quicker. Okay? Have you ever seen that that YouTube video? Here, actually, let me show you. I love this. Give me 1 second here. Okay, I was able to find the thing I want to show you. And this is a great example of convolution. This is why studying neuroscience can really help elucidate convolutional networks, neural networks, machine learning. So your job here is very simple. You have to count how many times a person in white is past the basketball. So I don't know if you need a pen and paper or what you need to do this, but just count how many times somebody wearing a white shirt gets a basketball. We should all be able to do this. We're all in graduate school. So you guys ready? Remember, count how many times. This is important. How many times a person in white passes a basketball.
The test of selective attention. Count how many times the players wearing white pass the basketball.
One, 2, 3, 4. I don't want to give it away, so I'm going to be quiet. Like 12, maybe 13.
How many passes did you count?
So guys, how many passes did you count? I should have made this a discussion post. 12, 14. The correct answer is 15. But that's not the point of this
answer
test.
Is 15 passes. But did you see the gorilla?
A lot of people that have never taken this will never see the gorilla before. So if you've taken this before and you've seen the gorilla, you know it's there. But if you've never taken this, something like 80% of people will not notice that there's a gorilla walking through the screen. They won't even believe me until you rewind the video.
Is from research by Daniel Simons and Christopher Chabris. And
so now, Richard, why did you show this to me? Okay, because that is kind of what a pooling layer does. That, at least in my mind, as a starting point, is what a pooling layer does. Okay, one second. Okay, so we have the convolutional layer. We got to make sure you guys can see my finger there. So the convolutional layer, flashlight. We're going through. Oh, there is we're looking at a car, or I don't know, person passing a monkey. There's a bumper. There's a tire, but we still have a lot of information. So a pooling layer basically takes that information and does a maximum, it does something, but it takes the features and makes it look smaller. It makes it less detailed, it blurs out things that are less important. So you're only focusing on what's important. Okay, the brightest spot in the picture maybe of the flashlight. Yeah, I guess that makes sense. It reduces the size of what you're looking at, keeping the most important features. As humans, we do this automatically. We don't even realize it. Hence why a lot of people did not see the monkey or the gorilla, person in the gorilla, walk through the video. So that's what a pooling layer is. And finally, at the end, we have a fully connected layer. What's a fully connected layer? A fully connected layer basically just says, hey, this is X. This is a car. You have a bunch of outputs. Is it a car? Is it a cat? Is it a bird? Is it a plane? And it connects all those end neurons. It says, yes, it's 90% chance it's a car. It's a 10% chance it's a monkey. I have a great demo of this. But these are the three main concepts of a convolutional neural network. Convolutional layer, pull detail out of an image. Pulling layer, basically focus your attention or pull the most important feature or the brightest feature. That's maybe not the max feature. It's kind of hard to explain. The convolutional or the fully connected layer is, hey, what is the output? Now we stack these on top of each other to get different types of networks, the ResNet, for example. So let's continue a little bit. Flashlight, person in the background, everything's connected. So layer one identifies fundamental attributes like edges. I don't know where I found this, but I love this. It took me a while to put this together. So we're looking at a picture and we can see, hey, look, it has edges. And why is that important? Again, we go back to science. There's a scientific experiment that shows that if cats never see an edge, they'll fall off a table. They don't realize there's a vertical drop. Yeah, you can look it up. If cats are raised in a completely, I think it is symmetrical, like cube, and never see an edge, they will fall right off a table. So layer one, basically we start identifying edges. Let's see if I can go to the next one. Oh, there we go. Look, it worked. Layer two, we add on. I guess I should add a space right there. After we detect edges, we combine these things, maybe circles or stripes, simple geometric shapes. We start designing. We start looking for texture, honeycomb patterns, checker box, tires on a wheel. See, we're back there. We couldn't really see they were tires. Now we can see their tires. Butterfly, people's faces. And see how we kind of just build up through these layers. Layer number 4, by the 4th layer, CNN starts to recognize more sophisticated elements. By the 5th layer, we start to recognize typically things that represent combinations of lines, circles, patterns, of the things in the past. And 6 and higher layer, we recognize complex shapes. So this is kind of how our human mind works too. We have grid cells, we have square cells, we have cells that recognize basically lines up and down, vertical lines. We have cells that represent circles. So anytime we see a circle out in the real world, we have a neuron that fires in our brain. Even if it's just part of a circle of a tire. Okay, so this is again wired after how we work. Just Google grid cells or place cells. There's a bunch of different things you can Google, but this is basically how our brain works. This is what makes it work so well. And you can kind of see it here. Here's another big picture idea. So see how we have this first kind of like little flashlight. Well, we don't know really what is it. What is that? I don't know. What is it? I don't know. Oh, hey, that's an eye. As we kind of go through the layers, we recognize that that's an eye, but I can't really tell if that's a face, if it's right side up. Is it a human eye? I don't know. And as we keep going down, we recognize that it's a face. Now, it doesn't have to be a face. It can be a stop sign. It can be a car. It can be Japanese characters. The idea is the same no matter what. It's just easy for us to understand a face. Now, I know what you're thinking. I'm thinking the same thing. Why did I take the blue pill? Richard, why do I care? Why do I care as a business intelligence person? I might not be working with images. And it's true. Most business intelligence people do not work with, in terms of images to analyze. So why do you care? And it's a valid question. Throughout this whole course, I've really strived to ensure that what I teach you is relevant to the business world, not just some academic rigor. I've asked friends for demos on certain subjects, and they come back with these things that will never be used in real life. And it makes it hard. I really want to keep this class realistic. So why do I care? And here's why you care. So it's going to be kind of hard to explain how deep variant works. But let's think about genetics. And this is not entirely true, but the premise is. So our genes are A, C, T, and G. That's what makes up all genes in humans and I think everything else in the planet. So we have 4 genes. Well, what else do we have 4 of? Cyan, magenta, yellow, and black. CNN is really good at detecting patterns. Well, variants are patterns of disease. So what if I somehow took all the genetic information, it's just instructions, A, T, C, G, in some order. What if I was to take that and run it through convolutional network? With a convolutional network, be able to create a picture, even if it doesn't look like a picture to me, and maybe it might look like static. Would the convolutional network be able to make a picture and detect disease? And the answer is yes. And not only does it do this, it does it very, very, very well. Does it very well. So the point is that convolutional networks don't just work with pictures and videos. They can work with tabular data too. And when they work with tabular data, when I mean tabular data is like a database, they can detect patterns beyond most neural networks, most RNN. They're very, very good at detecting patterns, so they can put it in a picture. Let's see if I can find deep pic like this. Okay. So again, they're not pictures that we're going to be able to understand, but the computer knows the difference. And so deep variant is able to detect genetic variances cheaper, faster, and better than traditional methods as of 5 years ago, 8 years ago. Now it's kind of changed, but that is one huge reason why we care, because it's not only about pictures. We can find ways to map traditional data to a convolutional network. We're able to really advance our pattern recognition. COVID just happened. I mean, the last 2 or 3 years have all impacted us in many different ways. A lot of businesses started using face mask detection and well, not in images and video, I should have put video. But basically, hey, is a customer wearing a mask? Yes or no? Amazon Go stores. How many of you have heard about Amazon Go stores? Amazon Go stores. There's a great skit on Saturday Night Live you guys should look at. So Amazon Go stores are a very simple idea. What if there was a store that didn't have checkout? You just pick up and go. So that's kind of how Amazon Go works. Okay? You just go to the store and there's no checkout. It just knows, using machine learning, it knows that you picked up a ham sandwich. It knows you picked up a bottle of water. It knows kind of what you did. So Amazon Go, and that's going to be maybe not necessarily Amazon Go stores, but that type of information is becoming more and more valuable to businesses. I was reading an article this morning, I haven't even included in here, about Clearview and how they're using Clearview at stadiums, Taylor Swift concerts, to detect terrorists, criminals, and how this has been on the rise over the last 3 or 4 years. And how, hey, let's say you have a warrant, they're thinking about putting police at like concerts using facial recognition to detect criminals a lot quicker, maybe old child support. So again, CNN, and there's a lot of money in this idea. Object detection. So you have an assembly plant. Let's just go 100% business. You're making widgets for the Toyota car. You're making these little square widgets, and your widget is like this, okay? And you have to make sure that this widget is the same as last widget. CNN, medical image analysis. All of medicine. I don't want to say all that. It's a little vague, but a lot of medicine has been revolutionized by CNN and medical image analysis. I gave you an example of the flu or COVID and X-rays I did a couple years ago, and like I said, it is a huge impact. So I'm gonna post a couple of these. I guess if you want to learn more, you can do a dog or cat. There's also a couple others, a celebrity face set where we can detect different celebrities. There's that pneumonia detection. So there's a couple different ways to learn CNNs. For me, it's not so important that you guys learn CNNs, that you understand the big picture, and that, if you want to learn it, there's tools out there to learn it. The nice thing about machine learning is that there's a lot of tools out there. As long as you understand the convolutional, the pool, and the fully connected, big picture ideas. So here's how it kind of looks a little bit more in detail. And I think the very last slide, or maybe it's the next slide, I don't know, talks about different networks. And so it's how we interconnect these networks. Remember, with a neural network, it's just not one neuron. You don't have an input to an output. You have network connect to network. I mean, 1 million neurons are connected to another million neurons. It's a very messy, interconnected world we live in. And CNN is no different. So it goes through, I have a great demo I'm going to show you guys here in a second. I forgot about that. And then boom, boom, pooling, kind of figure out the most important feature. There might be a cloud here. We don't care about the sky. So we pull that, and we just keep doing it until we get information. Fully connected layer basically tells us, hey, it's a car, it's a truck, it's a van, it's a bicycle. Here's a big picture. If you can understand this, if you can explain it to your classmate, you understand what CNN is. I love this demo. There's 2 demos here I'm going to show you. I'm going to show you the CNN, and then last week I talked about GAN. I'm going to show you real quick GAN. That's kind of hard to understand. So here is, I'll post this too in this slide. Let me see. Load. Okay, so I guess you guys can see it. So this is a great explanation of a convolutional network. Okay, so there's that. But the thing is, though, we can click on any image and actually see it happen in real life. We get a little closer so we can kind of go over this. So we see how the kernel slides over the input channel to get the immediate results. Click to learn more. So you see how it actually, if you hit play, you actually see it working. You see why these are computationally hard to process. Remember, 64 by 64-bit image is really small. The iPhone 15 shoots, 8,000 by 6,000 pixels. So I mean, just infinitely bigger than this. But you can see how it you can see what it's doing. You see how there's a block right there and it's convoluting, the information. Well, then what we do from there is take that. See, I think you can click on this. Let me close this out. And you kind of get the output, the max value of that. Not really max value, but still. And we go on. We do that again. We do that again. We do that a couple more times. Hence the term, let me take a second glance. Let me look at that again. Sometimes we have to look at things multiple times. Each channel input gets a different kernel. Hover over to see the values. Now this kernel weights, there we go. And then again, we're just going to pool. This is a pool layer. Oh, it's not. The maximum values. Then the fully connected layer. This is a cool part. You can kind of look at this right here. And this tells us, hey, what are we kind of looking at? So let me go here. So school bus. Okay, so here's that softmax function. Now, if you don't know anything about math, and I said, hey, I want the pathway that has the highest number. So -2, let's say, 5, 4, 6. Well, that's a pretty high number. So what's 6? A bell pepper. So we know it's not a bell pepper. Oh, 12. Look at that, 12. What's 12? 12 is a school bus, and we had an input. I know it's kind of hard to see. We had an input of the school bus. We had 12, so that's the highest one. -11, so we know it's not a koala. We know it's not an espresso. We know it's not a red panda. You can kind of see, like over here, how it maximizes. So, sports car is kind of similar to a bus. 0.6. I mean, that's technically the second highest. And this one was also pretty high. What's this? A bell pepper. Probably the color. But you can see that all we're doing is saying, hey, this is the one that's most likely is. The same way inherently kind of our brain works. How many times, I know it doesn't happen often, how many times you've been out in public and say, hey, is that, oh no, it's not. Because again, your weights were incorrect in your brain. Okay. So we click on, let's click escape. Let's click on, let's just reload this. I guess, let's do, what's that? A smiley ball. So there's a red channel, green, RGB. Kind of see how that works in there. I'm not going to spend too much time on this because you can do the same thing. You can read below. It goes through all, these, kind of match what's the most important feature here. Let me look at it again. Let me figure out what the most important thing is. Let me look at it again. And then at the end, with our fully connected layer, what are we looking at? Like an orange ball. Here's orange. We hit softmax here, or whatever we're using here, softmax. So while I may not know what each one of these are, okay, -29, I know that's not right. So let's see, what do we have here? Oh, 12. 12 looks like the highest. 16 right there, 16. So let's see what 16 is. 16 says orange, right? Am I on that? Yep, see how it moves over there? It's so much easier to kind of teach this person. Sports car. What's that? That's school bus. That's koala. So see how 16 is the highest number? We've classified that orange as an orange by just breaking its features down and say, hey, what's most important about this? What's most important about this? What's most important about it? And we come up with that's an orange. And here's a little more in detail about that. So it's a great demo. I'll cover the GAN demo after this because I don't want y'all to get confused. Now, libraries. So since coding out a neural network from the ground can be complex, time-consuming, and just a nightmare, and you'll end up with hair like me, which is no hair. Companies, Facebook, Google, everyone has made libraries. Now, a library, you've used Pandas and you've used NumPy and MATLib. Libraries are just shortcuts to help you do things. Okay? So that's all these libraries are. They're shortcuts to help you do machine learning. So I just, pick a couple of more common ones. I think I have 2 slides here. TensorFlow, I used to use TensorFlow a lot. Now I've moved over to PyTorch. It doesn't really matter what you use. I mean, some might be better for some might be better for others. Keras, okay. Here's some more. The one I do want to mention is Fast AI. Fast AI is supported by Jeremy Harrison. Fast AI. I love their videos. I love the tutorials. He has a book out. I have it here in the other room. Fast AI. I made this. Yeah. He has a bunch of videos. Jeremy Harrison, I think. Jeremy. Really guy's name, but he's Jeremy Howard. There we go. His Fast AI, the way he explains AI, and the way he talks about machine learning is well worth a review. He's got a lot of videos. Sorry, I have to sneeze. Sorry about that. So his stuff's worth a look too. And again, it's just another library. I've used Fast AI. I don't use it necessarily in production, but to learn, I've used Fast AI. So that's a really good one. Microsoft's toolkit. So now, before we leave here, one last thing you have to kind of understand is models or networks. Now, these are just the way things are lined up between convolutional layer, pooled layer, convolutional layer, pooled layer, things like that. So, if we look at the human brain, the biological brain, the wet brain, the way we sense smell goes through a completely different pathway than the way we see things. Okay, so that's why maybe people with certain brain issues can still smell, but they may not be able to see. Okay, because they're different pathways. They're still neurons, and the neurons have to fire. They go through different networks, and that's all these are. The two, maybe three, maybe four that ResNet is or was really popular. I've used ResNet quite a lot. The Inception by Google is very popular in VGG. Now sometimes there's different numbers in and around them. ResNet 32, ResNet 50, things like this. Don't worry about that. Just know that they're just different layers, they're just different networks, different pathways. They still use convolutions, they still use pooled, things like that. So let me show you a couple of those things. So not that. Let's see what we have here. Oh, this is business reasons. Okay, so here is one of the some of the older networks. Convolution pooled, convolution pooled. Okay, fully connected, fully connected. So you see how one of the older networks, did I list? I did. Here we go. Has the interconnection right here. AlexNet, which I did, is a newer, I guess, more modern network. You see how it has more layers. Did I say, yeah, ResNet has 152 layers. It can't have more or less. So let's see, where's this? And if you see an image of ResNet network, I was trying to find a GIF for you guys, couldn't find one. You'll see how it gets complicated very quickly. Okay. But again, the idea is the same. Convolution pool, things like that. Different types, nothing here. So this article I want to cover real quick. It's just different reasons that CNNs are popular in business intelligence and why we might use them. Image classifier, search engine, recommendation system, those are all CNN specialty domains. Face recognition. So Facebook, it says, hey, is this your friend Tom? That's a CNN. Legal banking documents. So there's a ton of documents that are scanned or that are written by hand that aren't scanned in. They're not digital documents, creating a lot of problems. I mean, there's been banking for 2,000 years. There's been computers that really, digital internet for 50 years. So what do we do with the other 1,950 years of data? It's literally in a flat format we can't access. So we can use CNN, we can use OCR to try to digitalize those. And I mean, medical health care, risk assessment, not just in this, drug discovery, predictive medicine. So I think that is most of the CNN. So this stops the CNN part. Last week I talked about a GAN. And it's kind of hard to explain what a GAN is. I use the analogy GAN, fake $20 bill. I think that's a pretty common analogy. Images. Oops, GAN. Well, maybe not. Maybe I'm the only one that's ever used that. GAN. So in a nutshell, again, so I had a question about it. Basically, it generates an image, we say. Then we have a discriminator. That would be the Secret Service agent that says, hey, your fake $20 bill does not look very good. And the discriminator kind of feeds back data, says, hey, here's why it doesn't look good. Here's what a real $20 bill looks like. We're using the discriminator. So, hey, and here's your fake. It doesn't look very good. Okay. Well, I found a GAN lab. So cool. So if we want to make a circle, that is our goal, to make a circle. The generator is just going to throw a bunch of random data, kind of. And you see, hey, here, the machine says, go this way, go that way. This is how you make a better circle. So here's what it sends to the discriminator. The discriminator says, nope, this is not right. Here's a real. Basically, it looks at the difference and slowly, surely gets better at making better fakes. Or synthetic data. That might be a better word instead of fakes. You see how it just kind of feeds back through here? And over time, I mean, you see we're at 2,000 epochs, 2,000 iterations of this. And we let it go long enough, it will produce a circle that looks relatively good. Now, why is this important? So GANs hold a very important place in the machine learning world, particularly in artificial intelligence and business reporting, because a lot of times we don't have all the data we need. So we can make, I don't want to say make fake data, make synthetic data. Or maybe we want to share sample data. Maybe you're working as a consultant and say, hey, here's something I did, but you can't share the real data. Use GANs. You can use it to do, I mean, you do voice. There's all types of different things that GANs can do. Kind of hard concept to realize that you have two machine learning models competing against each other. But this is basically just making a fake fake image. And the discriminator, the Secret Service agent, as I used last week, says, hey, this is where it's good, this is where it's good, this is where it's bad, this is where you need to improve, and gives it kind of feedback. And eventually it will get better and better and better. So that is a GAN. Again, if you guys have any questions, please let me know. High-level things, convolutional, pooled layer, fully connected. Like I said, don't worry about these. Just know that there are a lot of different models out there. Don't worry about a lot of these. Just know that a lot of libraries, and to do CNNs has become very, very easy. It's a few lines of code nowadays to do a basic CNN. There's a lot of demos out there, cat versus dog, fully coded. You know, pneumonia detection at 92%. So there's a lot of demos out there. So again, that's a high-level overview of CNNs. CNNs are very popular in business. If a picture is worth 1,000 words, and we can understand that picture as a computer, we can make 1,000 times more money than other people that can't understand that picture. Hopefully everyone's doing good. Please contact me if you have any questions. Thank you.